Hey everyone, and welcome. If you're just starting out in chemistry, you are in exactly the right place. In this explainer, we're going to build your foundation from the ground up, and trust me, it starts way earlier in history than you might think. We'll cover everything from those surprising ancient roots right up to the essential tools you'll be using today. All right, here's our game plan. We're going to take a quick trip back in time, then talk about what everything is actually made of. After that, we'll get into the chemist's toolkit, tackle a really big idea, and then we'll wrap it all up with a little quiz to make sure it all sticks. Okay, first stop on our journey, the ancient history of chemistry. Yep, that's right. It goes way back, long before any modern labs existed.
So when you think of chemistry, you probably picture someone in a lab coat with beakers and bubbling liquids, right? Well, let's just forget about that for a second. The real story of chemistry didn't start there. It began with ancient innovators thousands of years ago. We're talking about practical arts, things like working with metals and creating medicines.
And speaking of ancient innovators, you have to look at ancient India. These guys were absolute masters of material science. Seriously, they had this practice called Rasayan Shastra, which basically means the science of materials, and it was mind-blowingly advanced for its time. They were developing sophisticated metallurgy, creating incredible dyes and pigments. You can still see the ones in the Ajanta and Ellora caves today, and they're still vibrant. They even figured out how to make soap. This was all hands-on, practical chemistry that had a huge impact on everyday life.
Okay, so all this talk about transforming materials from metals to paints, it all begs a much bigger, more fundamental question, one that's at the very heart of chemistry. What is all this stuff around us? What is everything actually made of?
And the answer, in a word, is matter. It's a simple definition, but it's huge. Basically, if something has mass and it takes up space, it's matter. The chair you're sitting on, the phone in your hand, even the air you're breathing right now, it's all matter. And that's what chemistry is all about, studying. And matter, as you know, comes in different flavors, or states. The most common ones are solid, liquid, and gas. And what makes them different? It's all about how their tiny particles are arranged. In a solid, they're packed together, totally locked in place. In a liquid, they're still close, but they can slide past each other. And in a gas, well, they're just flying all over the place, far apart and moving super fast. All right, so if we're going to study all this matter and its different states, we need some tools, right? And the most important part of any chemist toolkit is measurement. But it's not just about getting a number. It's about two absolutely crucial ideas, precision and accuracy. Now, these two words get mixed up all the time, but they mean very different things. Think of it like throwing darts at a dartboard. Precision is when all your darts land really close together. You're consistent. Accuracy is when your darts hit the bullseye. You're correct. You could throw 3 darts that all end in a tight cluster way off in the corner. That's high precision, but low accuracy. What we're always aiming for in science is to hit that bullseye every single time. High precision and high accuracy. Okay, let's put this into practice. Check out this table. We've got 3 students. Let's call them A, B, and C. They've all been given a sample that they know weighs exactly 2.00 grams. Their job is to measure it twice. So, take a second and look at their numbers. Who do you think nailed it? Who was both precise, meaning their 2 measurements were close to each other, and accurate, meaning their average was super close to the real value of 2.00 grams? Yep, if you pick student C, you got it. Look at their results, 2.01 and 1.99. Those numbers are super close to each other, so that's high precision. And their average? It's exactly 2.000. That's dead-on accuracy. That's what we're always shooting for. So, to make sure that a measurement in one lab means the exact same thing in a lab on the other side of the world, scientists all agreed to use a standard system. It's called the SI system, and it's like a universal language for measurement. These 7 units you see here are the building blocks, the foundation for pretty much every measurement we make in science. Okay, let's switch gears to a really mind-bending idea. We know everything is made of tiny particles, right? Atoms and molecules. But how in the world do you count them? They're literally invisible. I mean, think about it. It's a huge problem. You can't just pick up an atom and put it on a scale. You can't line them up and count them. It's just not possible. So scientists needed a workaround, a really clever way to connect the world we can see and measure with the invisible world of atoms. And their solution was a new unit called the mole. The best way to think about it is like this. You know how a dozen always means 12, right? A dozen eggs, a dozen donuts, it's just a word for a number. Well, a mole is exactly the same idea. It's just a chemist's word for a very, very specific number of things, usually atoms or molecules.
So what's the magic number? It's this one right here, called Avogadro's constant. It's 6.022 times 10 to the power of 23. And let me tell you, that number is huge. It's a 6 with 23 zeros after it. It's so big, it's almost impossible to wrap your head around. But that gigantic number is the key. It's the bridge that lets us count atoms by weighing them.
All right, we've covered a lot of ground, from ancient history to atoms. So let's do a quick check-in with a couple of questions to see how you're doing.
Okay, first up, imagine a student measures a 10-gram weight 3 times, and they get these readings: 8.1 grams, 8.0 grams, and 8.2 grams. So, based on what we just talked about, would you say their measurements are precise, accurate, both, or neither?
The answer is, they're precise, but they're not accurate. See how all the numbers are clustered really close together around 8? That's precision. But the actual value is 10 grams, so they're way off the bullseye. That means they're not accurate.
Okay, next one. Quick memory test. Do you remember from that chart what the official SI base unit for mass is?
That's it, the kilogram, or kg for short. That's the standard unit everyone uses.
You know, all of this really brings us to a beautiful idea about what chemistry really is. I love this quote from the chemist Roald Hoffmann. He points out that chemistry isn't just about memorizing the periodic table. It's about the creativity, the transformations. It's about the infinite variety of molecules that you can build from those elements.
So I want to leave you with one final question to chew on. We've established that everything is made of atoms and molecules, and we even have this crazy way to count them. So what do you think is the single most common, most abundant molecule inside the human body, inside you? You don't have to answer now, but just thinking about it, well, that means you're already starting to think like a chemist.